All right, we are live and we are live with so many people. Welcome everybody. Thanks everyone who's speaking today and thanks everybody for joining. We have, I think, one of our most exciting talks that we've had so far on these MLOps mini meetups. We have a lot of LLM content today. We have an hour and a half session. It'll all be recorded in case anybody can't stay for the whole time, but it'll be pretty fun live as well. I think I'm going to let everybody introduce themselves just because of how many folks we have speaking today. And we're actually just going to jump right into it. And then we'll have discussion and questions at the end. So just for intros, Thomas, you want to kick us off?
Yeah, hello, I'm Thomas, machine learning engineer at Rates and Biases. And I'm pretty excited to be here.
Hi, I'm Boris. I'm the trainer of Dayma and founder of Craiyon. I work mainly on image models and now becoming like large models. So I'm excited about these talks.
Sweet. Robbie?
Hey guys, I'm Robbie. I'm a founding engineer at Leap Labs. We work on interpretability tooling, and it's my job to take what the researchers build and actually sort of turn it into a product that anybody can use.
Awesome. And last but not least, Jonathan.
Hey everyone, I'm Jono. I'm a data scientist and independent researcher. So I kind of oscillate between trying to make educational materials and then doing some consulting.
Very, very cool. All right. I am super excited for us to jump into this. I'm going to take everybody off, pull Thomas in, and Thomas is going to kick us off.
I was initially going to present you another project I had about training tiny llamas, but yeah, I changed my mind because I've been working on another project, on a side project from our CEO, Lucas, actually built a small tool, and I want to share with you some of the knowledge we gathered during this experiment. So first of all, I work for Weights and Biases. Weights and Biases is an ML platform tool that helps you out to build your models, to train them, and it also has some tools for prompt engineering, LLM fine-tuning, and we are used it in most of the industry across different topics and subjects. So we're integrated with cloud partners, and we're a pretty well-established name for LLM, actually. So, yeah, from the perspective of a machine learning engineer, writing code and building models is an iterative process, an experimental science. We do a lot of trial and error, so that's why like Jupyter is so loved by the ML practitioner. And tools like Streamlit gives you a lot of power to actually visualize and experiment with what you are building. As I said before, we have a bunch of customers and across many industries building awesome games, making organic farming easier, making better medicine, or making customer support less frustrating. So these are some of our customers examples. But today I'm not here to talk about that. I'm mostly interested in talking about LLMs. So we have defined actually three types of persona from the LLM perspective. So we have the LLM creators, like people like OpenAI, like Meta, that are building these foundational models from scratch, gathering the data set and training on these big clusters. Then we have regular folks like LLM fine-tuners, the ML practitioner that's taking those pre-trained models from the hubs and adapting them to their use cases, like gathering some data from their specific use case and aligning the model to that data. And recently we have this new type of persona called the LLM prompt engineer, we will call it now, but it's this person that is using a ChatGPT or using OpenAI models on an API, or just serving llamas and then using their llamas to integrate AI into their own software. So in that perspective, I'm going to talk to you about a small experiment that Lucas built, and I came later in the game, but mostly helping him. I will show you exactly what I did, but this is a cool idea because it started from this, this is Lucas' daughter. I'm asking Alexa to play her favorite song, and Alexa giving back a recipe of milkshake or whatever. It's AI assistants are not great yet. That's my take. So from this LLM perspective, ChatGPT is amazing. How far away are we from building from these tools a cool Alexa, Postman Alexa? So we have some people trying stuff like this. Minecraft has this small tool that looks like this. This is another tool, but it's like a box that you can talk and everything's running locally. So you can talk and ASR model, and then you have an LLM that is running locally, and you have this tiny RockPi kind of device that is capable of running Llama on 200. device. You have the NVIDIA ones that are really fast. They are really cool to play with. So yeah, Lucas is talking and he asking like, ask OpenAI whales or fish, and the Autobot is like printing the answer on the screen. So yeah, this is a super simple front end, but behind the wheels, you have tools. Behind the scenes here, you have tools so it's calling a bunch of like skills. So this thing is extensible. So you can create like a skill that is get weather, and it's calling an API and grabbing the weather. You have a skill that is maybe Wolfram Alpha, and it's calling a math API, and then it's getting you the right answer. And then maybe OpenAI to ask more general questions, maybe a news API if you want to retrieve the news. So it's pretty extensible, and it's built on top of just this off-the-shelf tools. Like, so we have Whisper for ASR, then we have like an LLM that is transcribing and getting that maybe not that good quality transcription from Whisper and converting that to an API call like weather location equals Boston. And then maybe can speak back with the TTS model. But yeah, we don't use that yet. So what's the software stack? Yeah, as I said before, Whisper transcription, Llama or Llama. It will not end up being Llama, but yeah, Llama style model for this. But as you see here, like, yeah, Whisper requires PyTorch, it requires inference code in PyTorch, it requires a GPU, and yeah, model checkpoints for Llama, they're big, they require dedicated hardware, maybe a dedicated server engine like TGI, VLLM, whatever, requires a GPU to serve them. So yeah, not that friendly. And if we want to run them locally on a MacBook, we will need something more powerful. So enter CPP stuff. So Georgi Gaganov, this amazing Bulgarian developer that just amazing C++ developer, brought these tools in pure C++, no dependencies, and made running Whisper on your laptop and Llama on your laptop possible on CPU without any like dedicated hardware. Actually, on Apple, if you have an Apple device, it runs on Metal, so it uses the integrated GPU sort of thing they have. It's actually really fast, and it has quantization. It has like state-of-the-art techniques like speculative decoding. So I really enjoy these tools. So yeah, same here. I just record a video in case everything doesn't work. So yeah, Whisper is transcribing. This is just to show you that transcriptions are this is a recording of Whisper transcriptions, and it's just not very good. Like it misses some tokens. I'm not a native English speaker, so it's not that good with me, but so it's transcribing. I'm talking here and it's transcribing real time, but it's not, it's understanding terms like LLM community. So we have this small backend that enables you to configure what LLM you're using, what version of Whisper you're using, and we can debug like if this is calling the right tool. So we call other. I will explain later what's that. So this is basically what we expect, but latency matters a lot. Whisper is slow. The LLM is even slower. So yeah, it's a proof of concept. So how we ended up using Llama here. So if you take Llama, like Llama 2, pre-trained Llama 2, and you give like a dummy instruction, it doesn't work. Like below is an instruction, let's grab a task, that's the default prompt, and you try to actually what the weather in Boston, and without any context, like you get random answers. And this accuracy score I'm showing you here, I will detail more about this in the future, but it's a test data set we have. So they had 60 queries, and what do we expect them all to answer? And it's like 0% accuracy, of course, has no context, no chance of getting the answer correct. So what happened if we construct a prompt? Like let's do some prompt engineering. So we put some prompts here. You're an AI, convert a human, request function calls. We list the functions you have available. And we then like user query, what's the weather in Boston? Assistant, we hopefully get that weather locations equal Boston. So we're almost there. Like it gets you something that gold dot weather location equals Boston. That's the correct answer somewhere in there. But it also hallucinates a lot of random like links. I created that late for me. Like this is actually a query I did on my computer just to test if it worked. So this is not enough. Like I will need a new model here to parse this answer and extract whatever API call I need. So yeah, still 0% accuracy. So we realized, okay, let's switch to a better model. Maybe Llama Chat is more conversational. So just to put the picture here, you need the right model for the right task. This is an instruction and we want an output. So like using a pre-trained model like Llama, yeah, you should use an instruction model, a model that is capable of understanding like a system prompt and responding accordingly. So if we switch to Llama Chat, yeah, you need to format your prompt accordingly. So another, learning here is that you need to format the prompt accordingly to the models. And that sometimes it's not that easy to find. Like, yeah, you ended up reading the technical paper or maybe going to the hub and trying to see like if the formatting is there. Maybe you are missing an end of string token, nothing works. So yeah, you need to format your prompt accordingly to the model you're using. So this is the right formatting for Llama 2 Chat. So yeah, beginning of system prompt, it has this green token here, and then like end of instruction. And after the end of instruction, the model will start completing. So user query, what the weather in Boston. And this actually works 11% of the time, 1 out of 10. So as you can see here, this is almost the right answer, but it has this extra text. So function call, column, weather, location, Boston. So I would just want them all to answer that without the function call. So how do we remove that? We actually inject that into the prompt. So we added function call here to the prompt. So it doesn't have that extra. And when you do that, just adding that to the prompt. So looking at the generations from your prompt is really powerful. Like, so we look at the data set, we saw that, like half of the answers had that function call, semicolon, and the actual function call. So we added that to the instruction. And we got from 10% accuracy to 75% accuracy. So pretty good, no? So yeah, this is just a demo. I recorded this because I don't want to show you stuff that may crash. So we logged this data set to its basis. So we got a table. We are reporting the scores here, 75%. I also have like an accuracy lousy that it's kind of row score. So it's if the answer is contained in the generation. Maybe it's not correctly formatted, but it's contained. So I'm comparing here if answer equals to generation. And so I can quickly go through the 62 examples at this, 62 examples and see what the model is getting wrong. So as you can see, the others are most of them correctly formatted. Something is like KTVU, it's trying to create news and shouldn't be doing that. So this is actually good. Like, yeah, as you can see, sometimes location, it's trying to call weather and location is not a skill that exists. Other is like in uppercase, should be in lowercase, but I think we are almost there. So yeah, next step, it's 75% accuracy is not great. So can we improve that? So one thing we know is that if we add more context into the prompt, normally the models get better generations. So what you have different levels, like dumb instructions that you give like context, and like the most sophisticated, what they call like level 5 prompting, is actually giving examples of what you expect the model to do. So here are some examples of the queries and the answer we expect from the model. And surprisingly, this decreases performance. I don't know, Llama Chat is maybe not tuned for that. So adding those queries, I would expect like, hey, I'm expecting this from you. It should be better, but it's actually worse. Like we go from 75 to 51% accuracy. So then enters Mistral. So Mistral is this company, French startup that created Mistral 7B. Ex-Facebook people, like it's a very similar architecture to Llama with probably a better data set and better instruction techniques. And they have specifically a Mistral 7B and a Mistral 7B Instruct that it's designed for instruction. So let's try that one. This is the model that scores higher on the leaderboard. It's equivalent to Llama 13B on performance. So yeah, this should be better. So if we put Mistral straight away with the level 5 prompt with the examples, 79%. So it's straight away better than Llama Chat. So this is our baseline. Okay, this is the best we can get with just good instruction prompting, with prompt engineering. But 79% is still not enough. Like this means that like 1 out of 5 of your instructions to your assistant is gonna be failing. So yeah, let's fine tune them all and close that gap. So yeah, fine tuning, just quick overall here. This is from Sebastian Rashkas Prizo. It's pretty good schema that like traditional training is like training the full model, full data set cluster. We're not going to do that. Second option is conventional fine tuning. So you take the full model, you train all the weights on the model, you end up with a fine-tuned LLM. But for a 7 billion parameter model, that's already pretty expensive. Like you will need, a lot of GPU for that. And so now we enter parameter efficient fine tuning and LoRa and all friends of LoRa. This enables you to train these models on smaller hardware and just train a small subset of parameters from the model. It's actually not the parameter from the model. It's like an adapter you add to some of the layers. And this enables you to train cheaply. Like in 1 hour, you will get like a fine-tuned Mistral 7. And do you pay a little bit of price and accuracy? Not really. Like this is like an any scale blog post. They did a very detailed analysis on like full fine-tune versus LoRa, and yeah, it's almost the same performance on full parameter fine-tuning. So why do full parameter if we can do LoRa? And yeah, GPU memory, this is a little bit exaggerated because you can do, mixed precision training lower than 40 gigabytes on the 7B. But yeah, this is like without any tricks, you are out of memory if you don't have one of these shiny 80 gigabyte GPUs. And with QLoRa, you can actually train on a V100, like in a 16 gigabyte GPU. But you need a data set for that. So let's construct one. These are the prompts and what we expect. Like, what is the latest news? You should call the news assistant. Any news about astronomy? You should call the news assistant with topic. So we manually create like 4 or 5 of them. And then we go ChatGPT and we ask ChatGPT like, hey, you are a voice. We are training a voice assistant. Here are some examples of the news thing. Create me more calls like this. And one quick win here is that OpenAI gives you the schema, like function call, so you can explicitly tell how you want to format that data set. And I encourage everyone to use this. Like if you're going to use ChatGPT, OpenAI's tool set to build data sets, use the schema so you can format your output data as you want it. So here I want like input a user, output assistant. So I get that straight away, like a data set that is a JSON format compliant, and I can straight away train my model on top of that. So I manually create most of the data set. Like I was running the queries, like generating 10 at a time and just filtering, because like for LoRa fine tuning, it's better having less data that is high quality than having a lot of bad data. So 600 examples, fine tune, 98% of accuracy from Mistral. So basically the model is most of the time correct. I think it gets one wrong here. So that fine tuning helps you to get that 20% gap you were missing. And actually, Llama, it's a French model. It also speaks French. Like if you ask quelle météo à Paris, it gets you like weather, location equal Paris. So yeah, that's something we're not expecting, but it works. The code is public, so it's in Lucas GitHub. So Lucas/Auto. I'm trying to help him out, like cleaning up and making this better. So give it a spin. It's pretty lightweight. It just needs like, it has a server and maybe Whisper, and you have to bring Llama CPP and install them for your computer, and it will work. So that's the lesson learned. Like you can get a lot of from your model from good prompting, but that extra gap you will need for your specific use case, fine tuning is gonna close that gap. If you go to our weights analysis project, ConDB/GateCake/Auto, there's a bunch of failing stuff. I tried multiple fine tunings, multiple prompts, and this is an experimental science. I log a bunch of tables. There's a one-tail analysis tables that enable to compare the queries with the generations. And I built all those dashboards. You can see them on report list, and you can see like I did like ablation studies. So it's building a small project like this and trying to align your model to a very narrow data set, like calling the right function call, gives you a lot of insight on how this thing could work. So, and the repo, there's small resources on the bottom, so encourage you to check them. And we built recently a training and fine-tuning course with a lot of people from the community and experts and leaders on this, like Jonathan Whitaker, Max Surfing from Meta, and Wen Yang, Derek, and Yayu. So I encourage you to check our course, 1db.me/LLM course, and ping me on Twitter or or Discord if you have any other question. I'm mostly fine-tuning stuff right now. So that's all for me, and thank you. And yeah, thank you, Lucas, for building this and bringing me on. It was really fun collaborating with our CEO.
That was really, really awesome. Thanks so much, Thomas. You have a couple of questions from the chat, but just wanted to call it. I love that you can see all of these experiments and weights and biases. That's really cool. I'm definitely going to check them out. I love that. We had a couple of questions. So one person asked how you were measuring accuracy specifically.
Yeah, here in this case, this needs to output an exact function call. So it's just like a string comparison. Because because I don't want to post-process the output. The LLM should give me the answer straight away. That's why I have this like lousy accuracy score that is like, I'm just checking the capabilities of the LLM. If the function call is somewhere there in the generation, but it's not clean, I will find that as correct also.
Got it. Cool. And then one other person asked how you got to the 98%, and I believe that was through fine-tuning with QLoRa, right?
Yeah.
Cool.
Yeah, that's fine-tune QLoRa Mistral mode. Yeah.
Awesome. And last question for now, Bruno is asking if you could go into just a little bit more detail, a minute or two, about LoRa and other alternatives when you're fine-tuning your models.
Yeah, I'm writing an article right now on top of that. Yeah. So, yeah, most of the time you don't want to do full fine-tune because it's too many parameters. It's going to be expensive. And LoRa, I would say, is like the default because it gives you a good trade-off in performance. As you see the graphics from any scale, like from the full fine-tune, there's very little difference. And it's going to like run on one GPU. And yeah, I would go LoRa. And it's pretty easy to configure because LoRa is not doing anything to the training. It's just changing them all. And so you are adding these adapter layers, you're training them, and at the end you have to merge them back into them all so you can inference with them all. So yeah, I will probably do LoRa. And then QLoRa came more recently, and QLoRa is basically LoRa with a faster forward pass because it's like using I would say degraded model because it's using a quantized version of either Llama or whatever model you're using on the forward pass. So if you can use LoRa, I would use LoRa. If you have a really small GPU, maybe QLoRa is the best solution because the forward pass is still going to be expensive on these models. So yeah, you have good libraries to do that. You have Axolotl, you have transformers with PEF. So you don't need to implement any of that from scratch. Actually, fine-tuning LoRa, like Mistral LoRa, is, I don't know, less than 80 lines of code.
So yeah, it's become so easy. Transformers and Hugging Face has really changed the game there.
Yeah, I think you need to spend a lot of time, and most of the time is formatting your data set correctly, like making sure that the prompts you're injecting in the model are formatted accordingly to what the model expects. So visualizing that, decoding a couple of batches is super important before launching a training. Like finding a training script on the internet is easy. Like you have libraries that do that for you, but being sure that your data set is formatted correctly. Then when you are running evaluation, you need to like remove the answer. You don't need to forget that like if you are doing packing or stuff like that, you need to put like end of string tokens at the end. So all these details are very important. And I would say more important than just training because training, the library is going to take care of that.
Yeah, exactly. Well, awesome. Thanks so much. We're going to keep it moving, but we'll bring everybody back on to the end for additional questions. Okay, awesome. So we're going to bring in Boris. And Boris, you ready to go? I think whenever you're ready, just kick it off.
Yeah, I'm ready. So hi, everybody. Today, I want to talk about some recipes for training large models. We now use larger and larger models. What I call a large model is already when you get above like 1 billion parameters, it's pretty large. A lot of issues happen above that size. And so the goal was like, as we train more, try to share a bit some knowledge on how to train them, what kind of failure you can get, how to solve them, and make it a bit, bring a bit more knowledge to that. We see a lot of results about what's the performance of the model, but we don't see a lot about the struggle of training it. So quickly, where do we use large models at Craiyon? So Craiyon, for those who have not used it, it's an image generator model. So you type a prompt, like here, for example, I typed a house with Christmas decorations under the snow. trying to be in the theme of what's coming up. And you get images like that are based on the prompt. And it's trained on seeing a lot of pairs of captions and images. But to have like good quality results, you need a lot of parameters. Typically, already you pass that threshold of 1 billion parameters. Below it, it's kind of hard to have good results. So we use that for text-to-image. We use them also for training clip models, quite large, that help us index images, do some kind of image recognition. And we use it also, we use also large language model for like processing the prompt and trying to get more information out of it. So the first thing I want to say is like you shouldn't make your own model if you don't have to. Training a large model is not really fun. There's a lot of struggle along the way. So if you can avoid, don't do it. Typically, you will need more compute resources. You will need more time. It will cost a lot. As I said, there's a lot of trouble training them because you will get extra instabilities that don't exist on smaller models. There's not a lot of public knowledge on it. And also you have no guarantee of success. You can spend a lot of time and you see all the models that succeed. That's the ones we talk about. But they're actually a very little fraction of the models that are trained. As Thomas said before, he had a lot of failed experiments. For every model we train, we have like 90% plus models that don't work at all. And so if you don't have to train it, don't train it. Then if you can, you need to start by the most simple things based on your application, but try to maybe leverage a public API. This is very easy. So like the OpenAI ChatGPT API. The prem that you will have on them, the reason you could change is maybe the cost is high. You have a lot of inference on it and it costs a lot. And you think maybe you could save it by having your own model or managing it yourself. Maybe you can have performance issues, like the latency is bad. It can happen, or you cannot do enough requests in parallel. That can be an issue. One other issue is it's non-customizable. If you need a very specific use case, having one of those generic models that exist won't necessarily work. So you may need to make your own model. And the last issue is when you work with sensitive data, or if you want to keep your information a bit private, you don't want to use a public API that can have access to all your calls and all the inputs and outputs. The next step, if you cannot choose a public API, is to try to see if you can leverage open source models. So that way, that's the best. The list of open source models is getting bigger and bigger, and they are getting more and more powerful. So if you do image, you have a lot of version of Stable Diffusion that may fit your needs. Depending on the size, depending on the quality you need, depending on style, depending on your inference, you can choose maybe one of the models. There's the Llama models, the Mistral model, the models trained on top of Mistral, like Zephyr, which is pretty cool in Swift model too. They also come in many sizes, so you can choose what you need. What is interesting when you leverage the open source model, you have all that inference infrastructure that come with it. So for example, you can do low precision, you can limit the context, you have easy deployment, with the VLLM that already exists. You also have all the people that hack the models to work on specific platforms, like the Llama CPP, for example, that is good for the MacBooks or even other devices, but you can benefit from all of this. So if you can leverage one of the open source models, just do it. And then you have all other scripts that come for all type of applications and fine-tuning. If you go to the Hugging Face repo, we'll find pretty much a fine-tuning for every possible technique that exists out there. So I would say try to leverage those in priority. The next part is like, you cannot make your own model basically all the time. Sometimes you will try to make it, but maybe you need to stop before you even start. So you need to be aware of a few things, what resources you need. So you can evaluate first in terms of compute resource and budget. It will depend on the model size. So you have ways a bit to see what performance you will get out of a certain model size for your application. the easiest way is you look at, there's often a similar application to what you're doing. So you can see what performance they have, or there's like a evaluation benchmark, and you're like, I'm really close to that benchmark. So you can predict a bit what kind of performance we'll have based on a certain model. Once you know the model, you can have an idea of what the training budget will be. And if you train the model from scratch, it can cost a lot. Sometimes you have a small model, maybe it's reasonable and you can get a better performance. But you can also estimate on the papers that you will see how many steps you will need. Then you see their inference. Often nowadays they report even the number of flop that was used for training. So you can have an idea of what was the budget to train the model, which is great. As long as you can reproduce the code, and as long as often in the prem what is reported is how much compute was used to train the model. It's not the total compute budget, because it's only of that successful experiment. There's not the report of all those ones that didn't work. So it's something to keep in mind too. And then, so you need to have the knowledge to do that model. You cannot just say, I'm going to pre-train a model. Training a Llama model or Mistral model is something really hard, even more if you want to do it from scratch. A lot of that knowledge is still not really public. You have more information on the data set nowadays, not all the time. And you don't have, there's no training script for those models, as far as I know, for pre-training them. And the last thing that's very important, you need data to train your model. Sometimes you can have smart ways, like Thomas said before, where you can use ChatGPT maybe to generate your data. Sometimes maybe you have a very specific niche application and it's really hard to gather the data you will need. So you need to keep in mind how much you need to try to estimate how much data you can get and what are the quality that you can attain. And if it's not high enough, there's no point in trying to train your model even more from scratch. The last thing is basically when you decide that you're going to train your model, you should try to avoid training from scratch. And the first thing that I would do is I would try to see on existing model what results I can have. And I will follow a bit the same logic. It's cool that Thomas had this presentation right before, because that's a bit what he did, So you start with prompt engineering. That will be the first step. Then you will do few short examples in your prompt to see what performance you have. So you add more examples inside of the prompt. Typically, you get better results. Apparently, it's not all the time, but typically you will get better results. And there's another technique, which is using retrieval augmented generation. It's a bit harder to set up, but the idea is when you provide a prompt, you have a collection of documents that you prepared, and the model will retrieve the most relevant documents and inject them in the prompt to try to give you an answer aware of the context that you asked. So it can improve performance. It's a bit harder to set up though. And then the next step is try to leverage fine-tuning. I would definitely try to do fine-tuning before training my own model. The reason it's going to be much, much, much cheaper, several order of magnitude. You have really optimized methods for it, which are all the LoRa-based methods in which you just train a small amount of parameters, a small amount of new parameters versus the entire model. You need much less resources. The only problem when you do fine-tuning, in the end, you're still limited by the capability of the base model. When you do that, the model basically becomes better at retrieving relevant knowledge. So it kind of prompts the model to retrieve samples in the right space of its knowledge. It doesn't really create new knowledge. It's just better at retrieving it. So your accuracy will go up, but if your base model, for example, and no clue about French, it's not suddenly going to learn French. So you're limited by the base knowledge of it. And the models that are publicly available often are smaller. They try to get a lot of knowledge. So when you have specialized knowledge, you can build a data set so that it learns it, but it's always better when that knowledge has been in the pre-trained model. So now we went through all the reasons why you shouldn't train your own model. and you decided, okay, let's train my own model. So how to do that? The first part, you should spend a decent amount of time in a research phase. Look at a lot of papers linked to your applications. Often you will realize that they all leverage the same ideas, and those common ideas that are in every paper, it means they're good. Sometimes you have like ideas that are a bit novel and that are unique to a paper, and you don't see them a lot. They may not work. Maybe people have just not explored them enough. I wasted definitely some time being excited on some ideas that I saw in some paper, and in the end, I didn't have good results. Maybe I didn't implement it well. Maybe the result was a bit overhyped. I don't know, but there's definitely something common in the paper. They all use like transformer models. They all use similar type of architecture. They all train a certain way. That, those are like clear, robust basis to train the model. When you start training, you need to do a first prototype before training your own model. When you're going to do your first prototype, I always recommend to leverage as much as possible the open source ecosystem. You will see some data sets, some models, some code for training. Cool code, I like increase transformers. They have a chain script for everything. Otherwise, I want to do something different on GitHub of Lucid Dreams. Yes, pretty much all paper were produced in a separate repo, so it's pretty nice to use. You would use a small model size, and at this step, you don't want to be creative. You want to have a baseline that you can compare on later, because maybe your model will not work and everything. Maybe my architecture is bad, maybe something is bad. You want to have like as little chances as possible for failure. You just want a model that works a little bit, and that will be your baseline. Once you have done that, you want to experiment very fast and keep track of results. So to experiment fast, the first thing you need to have a small model. Small model will give you a quick feedback. If you have a small model, typically, even for me, when I train image models, I want to know within 1 or 2 days, is my idea good? Some models may require weeks to train. And I cannot wait weeks to realize that my idea was bad. And I want to explore different things. So you want a fast result. So in that case, you need very small model. And when you increase the scale, I like to increase in 3 to 10x increments max, because more challenge happen later and you don't know why they come from. So it's nice because you solve problems little by little as they appear. During that step, you need to test everything: data loading, training, validation, model checkpointing. You need to already use inference. You don't want to just look at your training loss. You want to really use the model as you plan to use it in production, so that you can see, is it working at all? You write down and you test all the ideas you had in mind as much as you can, and the one that interests you. And what I do as I create experiments, I add different model parameters. So here, for example, you see I add the config parameter for LN positions, add one for use sub LN init. It was different ideas that I tried. If you try something new, don't hesitate in putting something that is even complex, idea, blah, blah, blah. But you want to be able to retrieve them easily and compare runs conveniently. So whatever your idea, whatever thing you do differently, just add a parameter for it, log it, and you'll be happy to be able to compare it later. As you do experiments, you're going to do a lot of runs, and sometimes maybe we try just what happens if I remove the bias, or what happens if I do that. You'll have so many experiments that over time you forget your conclusions, you forget why you took that decision, and you go back in time. So me, I try to, as I get a conclusion, I try to write it down, and I also put what graph brought me to that conclusion. So I create report along the way. It's easy on weights and biases because you just select like 2 or 3 runs and you add to report, and it adds me directly that graph. I select those runs, I add it, and then I add a tiny note above, this means that I should do this particular setting. Some of your conclusions work mainly on your problem. There's no universal truth. So it's something important to keep in mind. There's some architecture worked really well on some of my models, and some other models, they worked less. So it's important to to check, because maybe on the paper they tried an idea that worked really well for their use case, but won't work on your use case. So do your own comparison. You need to create a benchmark really specific to your application. Don't test on something that you won't use in the end. Test it on what is your actual metric. And the last thing is really this is the only moment to play. So whatever you have in mind, whatever you want to try, it's the time to do it. Don't do it on the large model. You will waste compute. You will do it for nothing. Maybe it will fail. You won't know why. If you want to play with your model, it's now or never, I would say. I'm going to show you a quick example of how I do it. So like here, for example, I do my reports and I write down a bit all I tried. And then, for example, I do a little section bias index layer. And I put using bias index layers at 15% training time and alerts conversions. So I write really quick notes and add a section a bit for everything. And actually this report, I've been going back so many times because there's so much information that I just forget. I'm like, why do I do that here? Why do I put this type of layer here? And I never remember, and I go back to my report all the time. So it's very valuable. Maybe because I have limited context window. So I need to go back to those reports and retrieve the information, but it's very convenient. And I even add a little summary of all my findings. And I go back, why did I get that? What's nice to log your experiment is I can see, oh, here I got that conclusion because of these experiments. But it doesn't apply in my case because I want to do another experiment where maybe the conclusion would be different. So it's nice to write what are your findings and why you have those findings. You'll consult them later. Now I'm going to give some advice on model training. So if you have quick runs, let's say you decide to fine-tune the model, you should do a sweep. What is a sweep? A sweep is you do a lot of experiments in parallel, and you can optimize parameter to very little to very little degrees. But you need to do it mainly if your experiments are fast and you can afford to do it. So when does it apply? Like you have a small data set, maybe small model. You typically will just do a simple fine-tune, and it's a low cost for you. So in that case, yeah, do 50 experiments. If you do 50 experiments, the main parameters you should at least play with, I would say learning rate. Learning rate is extremely important. It's the main parameter, I would say. If you optimize one, it's the learning rate. The number of epochs is very important for language models. Typically, when you do too many, you can have a problem when you forget knowledge. So, but sometimes you can do more than what you train for. People in the past will do only one epoch, but for fine-tuning, you typically can do more. You have to play with it, and the batch size can have an effect too. So I would say at least those 3 parameters, just play with them and iterate on them, and try to use kind of a wide range, and you can optimize your model a bit. Maybe you get a few points extra accuracy. You'll need to spend your entire budget just because you have it. But do 50 to 100 experiments, it's good. And I like to refine my range little by little. So I start with like a broad range of learning rate, and I realize, it's my higher range a bit, you have better results. So then I just decide to do a new sweep within those range. I refine the intervals as I go. When you train your model, I'm going to go a bit into my recipe of what I use during model training. So for optimizer, my preference is shampoo. If you can, it's really, really nice. It avoids a lot of instabilities. It's magic. Then you use Adam, and then Adafactor is the worst. But sometimes you have enough memory, and if you do just a fine tune, sometimes a bad optimizer is okay. There's other optimizers, people do research on them. There's another thing that works really that well all the time. There's some research like from ML Commons where they try to really quantify what are the best optimizers. Typically, me, I stick to those 3. And when I can, I just use shampoo. And now they have good implementation both in PyTorch and JAX. So you can use it. Precision, you have float 32 is better than bfloat 16, which is better than float 16. The reason you go to bfloat 16 or float 16 is always because of memory or speed. If you don't get a big advantage in speed of memory, the FLOP32 is better. It can prevent some instabilities. So less things to worry about. No need to add new tricks, but it can add more memory. What people do typically, they will keep full precision on the model weights, and they will do lower precision on the activations. But if you want to be fancy, you can also choose on what parameters to do lower precision. Maybe, for example, attention parameters or the cross-entropy loss or things like that. You keep high precision and you lower precision on other parts of the model. That can help. Weight decay, I never use any. It helps a bit for the convergence at start of training, but in the end it helps a bit. So it's nice to decay to 0 if you use it. It's also good to avoid overfitting if you have a small data set or if you do just fine-tuning. Weight initialization for the large layers, typically you want smaller weights, it can have a big impact. You'll notice instability at the start of training. And often people put residual connections to 0. It doesn't matter too much if you use small weights, but I do it typically. Dropout, it's good also for stability and overfitting. If you train a large model, I don't care about it. I don't use any. Architecture, use whatever was used and worked publicly. That's your baseline. If you do your own MEDES things that I like, those are the main things I recommend to look at: norm former, including variants, QK norm, which is a bit like Swing V2, and removing biases. Those are interesting things to look at. Otherwise, if you see a model as trained, maybe try that instead. But I really like those stuff, norm former in particular, and the no bias thing. If you need to, you can do gradient clipping. So when the gradient is out too wide, you clip them, or some people even skip them. So they decide to not apply an update if the gradients are too high. Or you can use also EMA parameters. It's something used a lot, for example, in diffusion models. And when you have large model, you need to play with sharding. The best is when you can do data parallels. You have one model per device and the data batches are split over devices. This is very easy. Then you have, when you need to do model parallel, it becomes difficult. You have a repository that helps you do FSDP. FSDP is often really nice to try. So if you see good implementations, try to do it, but it can be tricky. By the way, it's easy in JAX. So that's why I like JAX. I can play with the parallelism very, very well. So that's one of the advantages. Limit the model based on the compute budget. I'm going to try to go a bit faster because I see I'm taking long. So limit your model size based on the compute budget you have. If you can use smaller models, do it because they will be also faster for inference. You need to think of how you're going to use them. There's no point in training a huge model if in the end it won't be realistic to use it in inference. So I test my inference model. I size it and I test it for inference in terms of speed and latency to design the model I will train before. But it starts with inference, not training. You don't want to realize later that it was bad. Batch size, use the biggest that you can fit. Typically, it's if you train a model from scratch, or if you train a large model, you want a large batch size, mainly if you have a big data set too. When it's too small, you can use gradient accumulation or gradient checkpointing. If you have to reduce your model size, if you can fit a big model, but you need to use a small batch size, your model most likely won't train well. So for image model, for example, you typically want to be able to fit 500 samples. For language model, often they fit 1,000 to 2,000 samples as they train them. If you can fit a large model, but you can fit only like 32 samples, you don't have a good model. Better to reduce your model and be sure you can have a large batch size. The learning rate, you need to, even when you have a large model, you need to optimize it. So I start with the one I had on my small model, and then I do ×3 increment. So if I have a learning rate of 0.1, I try 0.3 or 0.03. I multiply by 3, and I get the best one I can, and that's it. That's the one I use. During training, I have a warm-up, and I keep my learning rate constant. At the end, you can use a decay, so linear, cosine. You see, I even do manual decay. I like to do my manual decay because I like to see what happens to the model. It's easier to to realize what happened. And it's not an issue to do that kind of decay. There's no like problem of continuity or so. And completely at the end, you can do a linear decay. And sometimes instead of decreasing the learning rate, what you can do, you can also increase the batch size. For example, more gradient accumulation. It will have a similar effect than decreasing the learning rate. I kind of like doing that, to be fair, instead of learning the learning rate. Something you want to log the norm of the gradients and the parameters. And you want to see that nothing looks funky on your gradient norms. So if you have the gradients that seem suddenly to go very high, you'll probably have some instability. And you can notice on what layer it happened. So you want to log that. You want to log your training validation loss, and you want to make sure your checkpointing system is well in place. The two last things you want to do, as you train, you want to evaluate the inference. So me, I log sample predictions as I train to see how the model evolved. And I can compare from a checkpoint to the next if it became better. And also to experiment with your model, you want to be able to play quickly with it. So create an app very quickly. It's very easy. Use Gradio, Streamlit. Do a notebook if you need more control, but make a little app so that you can play with it, see where it works, where it doesn't work. Don't wait until model is trained, really. You want to notice, you want to play with the model from the start. And last thing, keep a training log. You want to save your training configuration, your loss metrics. You want to note any change you had between your runs and why, what it failed, when you resumed, the evolution of prediction samples. I'm going to open quickly an example. Here, for when I trained the large version of Dali Mini, Dali Mega, I kept a log, and you can see the evolution of the validation curve. You can see my training rate. Learning rate did a lot of funky stuff, right? I kind of moved it a lot, but I talk about the training parameters, model configuration, but I also add a little note of what changes I did, because you can see some gap before, and I say, here it's because I changed the validation set, because I noticed some issue. Here I changed to full precision training, etc., etc. So you want to keep track of these things. And the last thing is you want to record your learning. So what I'm talking about today, I put a report and I write the recipe, and I keep on updating it every month. I realize something doesn't work all the time, or I need to change other things. So I try to keep it, because it's hard to remember, and it's complex, and there's so many things that come into play that you want to keep track of all your notes as well as possible.
That was awesome. That was so much good learnings. Thank you so much. So we have one question, but I think that we'll save it for the end, but just so you can maybe noodle on it. One person was asking about how you think about building data sets for fine tuning versus if you're going to build a model from scratch, and whether or not you use large language models for it. So if you're going to use an LLM to build data sets, how do you do that? And if you don't, how do you do that? Think about that, and then we'll bring it back at the end. But yeah, thank you so much. That was really, really awesome. So much good knowledge there. We're going to bring in Robbie for our next talk about Leap Labs.
Thank you, Ben. So like I said at the start, my name's Robbie. I'm a founding engineer at Leap Labs. We're a tiny little startup split across SF and London. And our focus is on interpretability tooling. We're trying to create some new tooling with some new novel approaches that we think is an important way of looking at interpretability. So if you're not familiar with the term interpretability, basically we're all about trying to look at models from the outside in and predict their behavior in the real world. So we want to be able to answer the questions of, is my model going to embarrass me at some point down the line? Like, what has it really learned? And it's to help solve problems like this, right? We see this all the time in the news. There's models out there that are extremely sophisticated, built by brilliant teams that make mistakes in the real world because maybe they work brilliantly on the test and validation sets, but the real world is complicated, and it's hard to predict every single use case, every single potential failure mode for your model. So we think that interpretability is a sort of crucial step in the training pipeline that everybody should be doing to try and find these failure modes, biases, spurious correlations before you ship. And we'd like to talk a bit about how we do that. So there's actually a few different interpretability techniques out there. I'm sure many of you know about. Many of them will look at the training set for your model and try and find biases in that training set itself, which is great and that is useful, but it often makes assumptions as to what the model learned from that training set. There are some features that it may have picked up that you didn't realize it would pick up, some that you might have thought it would and it didn't. So it doesn't tell you the whole picture. There's other methods like mechanistic interpretability that look much more fine-grained inside the model at sort of activation layers and things like that, that are very important as well for understanding how these things work. But again, they're so in the detail that it's very hard to predict the real-world performance of the model and how it will react in deployment. So what we try and do is take the model almost like as a black box and really test it in a variety of ways to sort of get it to tell us what it's learned. So I'm going to use the example first off of image classifiers. In fact, I'm going to talk about image classifiers a little bit, which is strange for a LLM event, but we'll get to LLMs. There's two reasons for that. One is our methodology is most advanced on image classifiers at the moment. We're working on our LLM functionality, but also I think it helps to demonstrate some of the concepts that we want to introduce here and some of the terminology. So we all know how an image classifier works. You've got your model, you pass in an image. In this example, it might be a model that does some kind of human action classification. And from your input that you've passed the image in as, you get some classification out from the model, right? So what we try to ask is, what if this were to happen the other way around? So given a single classification that we're going to use as our target, i.e. running, what if we could run the model backwards and ask it, what is your perfect image of running? What image of running would contain all of the most important features that you have learned for the classification of running? And that will probably be the most likely image to be classed in that classification. And so this is what we do as a generative process. We keep sort of asking the model this question until we find that perfect input. And we call this the prototypical image in the case of image classification, or the prototype in general. This is the sort of the prototypical input for a target output. And it looks something like this in the case of image classification. So this is an actual model that does classification of human action. This is just a sort of a random thing that we found on Hugging Face. And you can see that the images that we generate through our process are pretty abstract. They kind of make you think about the old sort of Google Deep Dream sort of images. But with a little bit of practice, you can get some interesting information out of these things. So if I were to sort of draw your eye over to, let's say, running, here, using our running example, yeah, you've got a kind of an interesting interpretation of running. You can see some limbs here, there's a leg, there's kind of motion going from right to left. You can see the sort of the ground that they're running on, the grass here. And so this is kind of like a very sort of reasonable, vague interpretation of what running might look like. But then you think to yourself, this image contains all of the most important features that the model learned about this class. So grass, what's that doing there? This model has learned that grass is an integral part of running. And so from this, we can kind of build a hypothesis of how it might perform in the real world. Probably this model is going to fail to classify people running indoors or on AstroTurf or something like that. And under testing, we found that this was true. It was less likely to do that. So other examples on here. So maybe eating, you think, well, it's probably learned what pictures of just sort of food, generic food, but maybe it's not going into someone's mouth. Depending on your use case, that might be a problem. Clapping, you can see it's got a pretty good image of the hands and the body behind it. But it's definitely learned that like a body needs to be behind the hands. If it was just an image of hands on their own, it would probably not spot clapping. So again, depends on the use case of your model. If you're, got a camera pointed at a crowd, that's probably going to work. If it was more specific around the hands, that's probably not going to work. So really rapidly, you can come up with these hypotheses and start to sort of investigate them further. There's two more examples on here that we would like to point out, which are a bit more concerning. And this is where the sort of interpretability for AI safety part of things comes in. If you look at the two images here for dancing and fighting, you can see they're like especially abstract. They're sort of like a kind of cloud of limbs going in all directions. But what you'll notice in here is that the skin tones in these images are much darker than the other ones. And so this model seems to have learned that people with darker skin are more likely to dance or fight, which is obviously very worrying. Again, when we tested this hypothesis, we found it to be true. It was like 10% more likely to do that classification. This is something that you wouldn't want to deploy out into the real world, depending on the use case of your model. At best, this is an inaccurate model, but at worst, this is a dangerous model. It depends where you deploy it. And we always feel a little bit bad for the person that we're referencing here, for the model that we downloaded from Hugging Face. It's probably just like a hobby project, right? Like many things on Hugging Face. It's not going to be used anywhere too meaningful, but we don't know that. This, we think, is a really good example of how bias can creep into even the most innocent seeming models, and why interpretability is important to try and find these things before you ship. So that is why we are building out a tool set to help anybody to do this as part of their kind of learning toolchain. The platform that we're building is a Python library. So you would download this Python library from pip and you pass in a license key at the moment. I would say that we're in private beta right now. It's a free private beta, and we're like gradually sort of inviting people in to sort of try it out and give us feedback. We're very likely when we go to like fully open to have some form of free tier. So that's the purpose of the license key here. And then you can call this generate function to sort of kick off the model and kick off the process of analyzing your model. And the results will appear in our web dashboard, so you can analyze them and look at past results. One thing I will point out here is that this being just a Python library that you download, obviously, you can integrate this into wherever your training workflow is, whether that's a notebook or some other something else. But also, all of the compute is happening locally on your machine. We don't want to be like storing anybody's models and worry about the security concerns of that. So the model stays on your machine. You're just sending the results over to us. But we also we don't necessarily want to be like a full-on MLOps platform. We just want to put like good interpretability tooling into people's hands. So we're not precious about what dashboard you use to look at these results. So we proudly support weights and biases as a logging option. You can log straight to weights and biases with your API key. And actually, we use weights and biases every day internally. Our research team use it all the time to work on our methodologies. So that is what I want to show you today as like a very quick demo. So as we saw, the example that you saw earlier would look something like this. So you're passing in your model. You are passing in your class list for this image classifier of all of the classes it can classify. And then you're passing in a list of target classes, i.e. the right-hand side of that simple diagram. Here's the classes that we want to analyze. And then, of course, your weights and biases key. And we can actually, just to tempt the demo gods, let's try and run this and actually get some results out. So this is an iterative process. It will do inferences on your model, probably of the order of around 1,000 inferences. It depends on the model. It depends on the modality. So this is how it kicked off and started going. And then we will look on the weights and biases dashboard to see it has arrived. There it is. Cool. And what's nice is you can sort of watch the results live as they come in, as the iterative process sort of rolls forward. We've got hamburger, pancakes, waffles, much more innocuous examples than what we saw earlier. We're already getting something that looks kind of like a hamburger here. These are looking okay. Now we don't have time to sort of watch this whole thing complete from beginning to end. So I will show you one I did earlier. So here's a previous run, same classes. And you can see, yeah, we've got a pretty good hamburger. These look sort of quite naturalistic. But I just want to kind of go through a couple more examples to talk about, okay, so, from these prototype images, how can you sort of come up with a hypothesis and maybe test that and think about where your model might go wrong. I ran this one a couple of days ago, and one of the things that really jumped out to me were these two things here. So on the pancakes, that kind of looks like a blueberry. And similarly on the waffles, this kind of looks like a strawberry down here. And actually, I can sort of go back through previous iterations. And in this particular example, like on a previous iteration, the strawberries are a little bit clearer before it's sort of zoned in on the waffle. So you might think, okay, that's an interesting feature to have in the prototype, because the model learned that those two berries are integral to this classification. And might it use that to get confused over another class? So another sort of tool that we can use is this chart to understand that better. This is what we call an entanglement chart. This chart will show you how many features or proportion of features are shared between other classes that the model can classify and your target class. So if we look at that waffle example that we were talking about, we've got waffle at the top, and then working down the sort of the percentage of shared features here, you can see apple pie has a bunch of shared features with waffle, and also strawberry shortcake, and sort of working my way down to cannoli French toast. But yeah, strawberry shortcake, that's kind of suspicious since we saw a strawberry in this prototype. So going from there, you can look at these isolation images to go, okay, so given the sort of the top three of the sort of highest entangled classes to this prototype, what are the most important features in the image that would like drive it towards that classification? So on the waffles, you can see like kind of predictably this sort of grid pattern is really important here. But it is actually sort of highlighting a bit of the strawberry on the left. It's interestingly kind of grabbing the shiny bit, the sort of glint of light on the strawberry as something that is important to this classification. And you can see actually on strawberry shortcake over here, whilst it's picking out different parts of this image that might be possibly a strawberry shortcake, it's picking out the same thing on the strawberry there. So that's like, evidence that could be a problem, and something you might need to look at the training set to sort of to get out and retrain. So one final thing we could do to sort of doubly prove that this could be a sort of spurious feature is we can also run this isolation process on a natural image. So here I've passed it an image of actual strawberry shortcake, and I want to see, okay, given the sort of same process, the nearest most entangled classes, what does it find on this image? And again, if we sort of step through the process, we can see the next most entangled class is waffle again. And the feature of this image that would drive it to a waffle classification, albeit quite a low probability, are those strawberries. So you've kind of like proven your hypothesis for somewhat, and you might go through further testing and then start looking at training set and sort of work these things out, all to prevent that very embarrassing misclassification between waffles and strawberry shortcake. So you kind of see the concepts that we're trying to introduce here. You've got the prototype, which is the prototypical input that would result in the output that you are looking for. And then other tooling to just kind of help you along the way of going from, okay, I can see the features in the prototype, what features are important, what might get confused with other classifications, just to sort of nudge you into that insight of how your model might behave in the real world in a way that you might not have predicted and would only really become a problem later after you find out after deployment. let's talk about, now we've introduced those concepts, let's finally talk about LLMs. Going back to this super simplistic diagram, the point of research that we're now currently working on is trying to apply these concepts to large language models. So what does a prototype for an LLM actually look like? And how can it sort of give us information that we need to make sure that the LLM is going to behave in a way that we expect after deployment? And so in this case, maybe our target output is a sequence of tokens. It could be one token. Sure, let me show you how to do something bad, something bad that it's not meant to tell you how to do. What is the prototypical prompt that would drive it to say that? Is there even a prompt that will drive it to say that? And if there is, can we find it? Two things I'll say about this. One is kind of exciting. This is actually the first time that we've publicly shown any of the work that we've been doing in the LLM space, because it is brand new. I mean, it's only in the last few weeks that we've been putting something together on this. And so naturally, this really early days, this is very much an active area of research. But I'll show you a couple of different ways we're exploring in this space. So one would be something like this. So you would run a similar code you would import from some plain text. Obviously, the import doesn't resolve because it's not published yet. But you'd activate the library in much the same way, but instead of passing through a list of target classes for classification, you just pass in a target output that you want the LLM to say. And so in a sort of single token example, I've done an example where we've asked it to come up with different inputs that would result in the token boy, just the word boy with like a leading space behind it. And it's come up with loads and loads of different sort of 10 token inputs, many of them just bizarre, like no idea why it's gone down this road, that will force the LLM to just say that one token. But then we can start to find the frequency of the tokens in those prototypical inputs and count them up. And then we kind of get a word association for what that model what tokens are associated with that word. And we can put them in a nice kind of word cloud sort of thing. So there's kind of ones that you might expect here. Sort of boy is related to girl, sure. Naughty is an interesting one, teenage, some words that you might expect. But you might say, well, okay, that's great, but you could come up with words like this by just looking at the embedding space. Maybe you just find all of the words that are closest to boy in embedding space. But what we find is kind of similar to just looking at the training set from an image classifier, but bit different, is that doesn't give you the whole picture. What we have down here is a little chart of, on the left-hand side, split down the middle pretty much, are tokens that are nearest to the token boy in embedding space. And then we've joined that in with tokens that we've found through this generative process that seem to be associated with boy in the model's mind. And what you kind of see is that there's some tokens in here that are a little bit unusual. So like basketball is a strange one to appear in here. That seems to be pretty important, like not quite as important as girl, but like it's quite important, and it's it was at least worth appearing in this list. And so this kind of embedding distance is normalized between 0 and 1, and you can see, so girl is very close. Certainly the plural of poised is very close, but basketball isn't really close at all in embedding space. But through this process, we find that it is close. So it gives a hint of something strange going on here. I forgot to mention, by the way, this is GPT-2 that we ran this on. Something a little bit strange going here. Why is this token kind of far away in embedding space, but so closely related to the token boy in GPT-2's mind? What's probably an area of research that we need to dig into more is, understanding, okay, so what does it mean for real world behavior? It seems suspicious, but we need to sort of understand that better. But it certainly kind of tells us that just looking at embedding space doesn't give you the full picture. There's a second kind of methodology that we could look down to sort of think about what is a prototype in the large language model space, and that would be a multi-token output. So in this example, we've asked it to find the input that would result in an output that says, sure, here's a script for a phone scam targeting vulnerable individuals. Definitely something that we wouldn't expect this model to say. This particular model is Llama 2. I think this was generated from one of the smaller Llama 2 ones, so that's the medium one. And the input that we generated is, again, like almost sort of naturalistic. It's kind of script phone vulnerable individuals with some strange characters in here, but it's just enough to push Llama 2 into continuing on, not just creating this target output, but we ask it to carry on, and it goes for it. It creates a kind of script, and then it usually sort of finishes up by telling us like why this is bad, almost like it feels bad about having done this. And so with this methodology, we can kind of experiment with outputs that we would like the model not to say, and we can search the space for whether there's an input that would result in this. Now, you can kind of see that this obviously isn't a very naturalistic input. Nobody's going to sort of find this by accident, or they're unlikely to. And so again, this is what we're working on literally right now, is trying to not only search for a possible input, but a naturalistic input. And that will tell you something about whether somebody will find this by accident. So those are the two concepts we're playing with. But like I say, this is definitely an area of active research. This is the questions of like what is a prototype in large language models? How can this help us to predict real world behavior? How can we generate inputs that are a bit more naturalistic at all? So areas of active research that we're trying to figure out right now. Two more examples that I'll show you just to sort of really hammer home the AI safety aspect of this. So on the single token example, we were looking at the single token for boy. I also asked it to generate for the target token girl. And this is where, again, on GPT-2, this is where the results are more concerning. So it does something similar, like it comes up with a token boy, but you have ones that are a little bit more kind of edgy, sort of chick, sexy, kind of a little bit on the nose, make you cringe slightly. But you'll see that I've blurred out 3 here. GPT-2 came for the token girl. It came up with some very overtly sexual words that are sort of highly correlated with girl. That in this public forum we're not going to show, but you can kind of imagine. We all pretty much know why this is, because GPT-2 was trained on the internet, and the internet can be a pretty bad place. But the dichotomy between boy and girl here is definitely something of concern. But on the multi token output example, again, this is with Llama 2 that we've done this with. We asked Llama 2 for the output, sure, here's a racist joke for you. And the input that we generated before that that would trigger Llama 2 to say this is quite nonsensical. We don't know why these particular tokens would trigger this output. But unfortunately, it absolutely went for it. And it said something that's very offensive. See, I won't say what it is, but it kind of makes light of the slave trade. It's a really very unpleasant thing for it to say, and then kind of laughs about it, and then says, no, don't do this. We often see actually that it would continue on by telling you that that's not a thing that it can do, even though it just did it, almost as if it's immediately forgotten about it. It's very, very strange behavior. So this kind of is, we don't show this just for the shock factor. We don't sort of take any pride in that, but we show this to demonstrate that even in some of the most advanced models that are out there today, the behavior that we don't necessarily want and we don't expect it to ever go to is there. It can be triggered with sort of these kind of red teaming attacks. And what we intend to find is, can we get a tool that would generate a sort of a more naturalistic input as well, that can force the model down this road. So the points I'm hoping that, or at least some of the points I'm hoping I will have convinced you of today is that, interpretability tooling is really important for understanding how models might behave in the real world. What has it really learned? Does it have any biases you're not aware of? Any spurious correlations? And this is an important piece of the training cycle, so that you can find these things out before they are deployed. This methodology that we're introducing, the prototype, is a useful technique for doing this, for understanding what those features are from a sort of black box perspective. Certainly, it's early days for us for large language model research, but it's got exciting potential of the kind of things we can find. And yeah, even the most advanced models out today have biases that have the potential for exploitation that we certainly don't want to see. So that's all from me today. If this is interesting to any of you, I've got 3 links that you're free to look at. On the left is a research paper that we have on prototype generation for the image classification space. We'll almost certainly have one in the future for the LLM work when we sort of get more advanced down the road of that. In the middle is a link to a form to apply to our beta. We have some people using the tool already and giving us like really, really valuable feedback. And we're sort of slowly letting people in over coming weeks. So, if you're interested in this, if you think it could help you out, do follow that link and let us know. And we'd be really interested to learn about what you're working on. And finally, a good old Discord community. Everyone needs a Discord community where we can sort of discuss these kind of approaches. If you're interested in sort of upcoming releases for more large language model work, things like that, feel free to join the Discord. But I look forward to seeing you there and chatting with you all. But that's all from me for now.
Awesome. Robbie, thank you so much. That was fantastic. That was really interesting. I have a lot of questions, but I'm going to keep us moving because we're a little bit over. We called it a summit for a reason. We have some really awesome talks. So I think we're just going to jump right into Jonathan's talk.
Great, thanks. And just to mention, like, if you want to ask questions while I'm presenting, because I know we'll be a little short, feel free to put them in and someone can interrupt. I'm going to be talking today on what the Kaggle LLM science exam competition can teach us about LLMs. And so this is going to be just a lightning overview of some key takeaways from participating in the competition and using it as a test bed for various ideas. And you'll see that a lot of these ideas will line up with some of the earlier talks. There's a lot of formulas that are consistent across projects here. Okay, so let's start with what the competition was. The challenge involved answering these multiple choice science-related questions. And specifically, they'd been generated by GPT 3.5 from Wikipedia pages. So they would show the model a section of Wikipedia. They had some selection criteria for like sciencey articles, and they'd say, create a multiple choice question based on this. They didn't share exactly the prompt they used or the strategy, but what you ended up with were these questions where you have some sort of target question and then 5 answers, often very close to each other. The correct answer often very verbatim from the article. So the goal was to say, can you create a model that can run without access to the internet? So you can't just use GPT 3.5. Can you create a smaller, more self-contained model that can answer these questions? And they framed it as kind of a like small open model versus big closed model, which will win situation. But really, it's also just a good problem to play with. Like, what is the state of the art for solving this kind of task with LLMs? So to start with, without any training or fine tuning or any advanced techniques, the first question, the first idea you might have is, well, can we just ask the LLMs to do this? Sure enough, you can. So here's some baselines that I did, sort of reran just before this talk. A 7 billion parameter model, about 50% accuracy. And the competition had its own metric, but I'll use accuracy here just for easier understanding. Scaling that up to a much larger model, something like 75% accuracy. GPT 3.5 was about 70% accuracy, although caveat we'll talk about. And GPT-4, 84% accuracy. So far, nothing too shocking. If you ask the model, they do pretty well. These models have a lot of good general knowledge. Bigger models tend to do better. But okay, we should ask the question, like, how exactly are you asking? Because as Thomas showed, changes in the prompts can have huge variability in performance. And so this is kind of the baseline that I'm showing in that previous slide, effectively just saying, answer with A, B, C, D, or E, here's the question, and then looking for the response. And this is fine, this works. 85% accuracy is a hang of a lot more than I would get on those questions. They're not general, like you would notice if you did science in high school questions. They're very, very specific, hyper niche topics from the depths of Wikipedia. So very impressive that works at all. But I wanted to dig in and explore, like, does the way you ask that question matter? And the answer is, of course it does. So if you take now Mistral, I noticed very early on that if you use a base model, like just the Llama, like not tuned for chat or anything, it's pretty appalling, like more like 20 or 30% accuracy, just above chance. But if you switch to something that's been instruction tuned and you give it reasonable instructions to say, here's 5 questions, which is the right one, and you look at the raw like probabilities for the letters A, B, C, D, or E, suddenly you're at 60% accuracy, and this 0.74 is the metric from the Kaggle competition. Giving all 5 options and then saying, is A the best, and looking at the logits for yes versus no, bumps that up to 65% accuracy. Doing 5 separate calls where you do, or more than 5 separate calls where you do pairwise. A or B, is A correct or is B correct? Which is the one that's correct? And like accumulating those pairwise comparisons, now you're up to 68% accuracy. But then the shocker, the best, going one at a time through the 5 possible answers and saying, here's the question, here's a possible answer, is this the right answer, yes or no? And then comparing those probabilities across the 5 different answers. This is with a 7 billion parameter model. We're up to 70-something% accuracy, a score that would be, very, very high, at least early on in the competition. Yeah, and so it was very, very interesting. If we go back to our ones here, the headline is now, open model Mistral beats GPT 3.5, but really it's just clever prompting can boost your score. And if you applied those same techniques to the larger models, you get equivalent boosts in performance. Okay, so shocker, not too big of a takeaway so far. Now, evaluation. I should mention that, in most situations, you're going to have to be creating some evaluation that meets your needs. Like Boris said, you're going to have to create your own custom benchmark. The nice thing with the Kaggle competition is that you have the ultimate metric, which is like, do you win the competition? Where do you place on the leaderboard? And often relatedly, like a validation set that's open that you can use to measure that yourself. But there's a few things that are worth highlighting in the competition, which are going to have parallels in real life. One, there's a distribution shift. So the sample that they give you doesn't necessarily match the private leaderboard test set. It's also fairly small, right? They have 200 samples, which is fine for getting a broad trend, right? If I think back to the evaluations I just showed, trying the different prompting strategies, it's probably correct that the ones that did better in that are going to do better on a larger test set. But if you have something that's 80% accurate, you only have 200 samples, and you score it on those 200 samples, you probably get about 80%, but there's variability, right? Like the smaller the sample size, the less weight you can put on a small difference. If I do 2 different models and one gets 81 and the other gets 79, well, that could just be an unlucky run for the model that got 79% accuracy. So I just wanted to flag there that, like, evaluation is important. And what we had to do, myself and my teammates, Jeremy, very quickly realized we needed a larger evaluation set, and we needed to be very careful to match it to the kinds of questions we saw, so that we got a smoother, like more reliable signal. So then a few days before today, like I think on sometime on the weekend maybe, OpenAI released their talks from the dev day. And so I blatantly stole one slide because the talk, which is a survey of techniques for maximizing LLM performance, it kind of gives a perfect overview of where we go from here, right? We've just started, we've tried some things 0 shot, and we've seen, oh, cool. If I can access the GPT API, great, I can get 84% accuracy right off the bat. If I can use a local model and I can look at the logits and I can do these extra tricks, that's like the prompt engineering, I'm doing a little bit better, and I've found a way to evaluate so that I can see, is this actually better? And this slide kind of lays out often the kinds of pathways that these projects typically follow from there. For something like Thomas's demo with the, what was it called? The Otto project. The issue was following a specific format. And for that, the fine tuning is like the perfect direction to go. For this competition here, there's a bit of a trade-off because we want to follow the format, but getting it to follow the format isn't too hard. We also want to have the right knowledge. And so there's a few different tricks and techniques that we can talk about. The first one, and the one that was key in this competition, is adding retrieval. So before even talking about fine-tuning, fairly early on, some people noticed that, hey, hang on, the framing of the competition is that these questions are derived from Wikipedia pages. And although our submissions have to run offline in a sandbox environment, there's no rule that says you can't just put all of Wikipedia with you in that sandbox environment and query that. And so sure enough, that's what people do. Instead of saying, here's the question, give your answer, packing in some sort of context through search or through different like embedding similarity measures, finding the relevant, hopefully relevant snippet of the article, packing that into the message that's sent to the LLM before the question. This gives you a pretty significant boost. So in this demo here, the way I got the context was with the web search API, straight away from 70% to closer to 80%. And yeah, obviously you can't do a web search in the competition. We had our own giant embedding for all of Wikipedia, lots of different tricks for retrieving the right things. But this was really interesting to me because I'd heard of retrieval, and obviously it makes sense. You can give the model context that contains the right answer. It's much easier to answer the question. But I had no idea it was such a nuanced thing and such a powerful thing, and this competition really brought that home. So some lessons: look at your data, spend lots of time like examining the retrieved bits of context and seeing if they're actually useful. Build good evals, and in the next set of slides, I'll talk about like creating synthetic data and how, in this case, you could pick a random snippet, generate a question from it, and then your metric could be, when I run my retrieval pipeline, do I fetch that same snippet? The top entries all did this. They did lots of evaluation, like which retrieval strategy is best. Almost all the top submissions in the competition actually, use multiple different retrieval strategies. So they're getting snippets from 5 different places, and then they're re-ranking them with another model that looks at which one's actually useful. Really, really complicated, as all Kaggle solutions tend to be. But it turned out this was pretty much the driving factor behind winning entries. And to many people's surprise, the winners, if you look at the top 10, it wasn't all giant models. There was everything from, an ensemble of deBerta models, 1.3 billion parameters, to 7 billion parameter model ensembles, all the way up to 70 billion. A huge mix, but all of them had in common that they did lots of work on the retrieval. And so for the competition specifically, there was tricks like you have the answers, and they're often quite verbatim from the article. So looking at the answers, not just the question, doing TF-IDF, which is like a metric that tends to reward verbatim searches. So not usually very good for retrieval, but very good in this case. Re-ranking, ensembling, using better embedding models, etc. So this is cool. This, it turns out, is very similar to what people see in real applications. So again, from that great talk from OpenAI, when you're working with the client, and I've got friends and colleagues who are in consulting, we all see these problems crop up again and again with clients. You start with some basic retrieval. It's not quite doing what you want. So then you add tricks like hypothetical document embedding or re-ranking, finding multiple solutions, and then using a larger model to reorder them, packing multiple examples into context. So just like iteratively improving the retrieval part, just like you would in old school machine learning, like iteratively improving the model, trying ensembles of models, trying different techniques, trying prompts. All of it comes back to experimenting, seeing how it does, that kind of virtuous cycle there. Okay, so that was one cool learning from the competition. Retrieval is actually really powerful. Another one that this really highlights is that synthetic data is, kind of like a cheat code almost for many cases like this. So just like, again, Thomas with his Otto project, and Lucas, we told how the competition created their data, and we can mimic that. We can send a request to OpenAI. We can use the function calling if you want to enforce a specific structure to say, here's a snippet of Wikipedia, please generate a question, and five answers, one of which is correct. Lots of prompt engineering you can do to get the right, only one answer correct, to get the right kinds of lengths and things to try and match the data. But what's cool is that you could also, with not many of those examples, because using the API costs money, fine-tuning a smaller language model to do this task, surprisingly easy. The trick with a lot of these insights, and I think the first paper that showed this was maybe like instruction back translation or self-instruct, they realized that answering a code question or a general knowledge question is hard, right? The model might not have the capability to write that code, but showing it some code and then asking it to come up with a relevant question that would generate that code is easier. So like the reverse task is easier. And same thing with us. Answering the question without any context is very difficult, but being shown a paragraph from Wikipedia and then creating a question based on that, tells that that's much easier. And so then you can kind of bootstrap your way to the reverse task by generating a bunch of data in the easy direction. Here's an article, make a question. Here's an article, make a question. Very easy to build up a catalog of data. And again, the plea that I'll be repeating several times through this talk, please look at your data. If you're going to be doing this kind of synthetic data generation, fine-tuning, especially like the parameter efficient and sample efficient, QLoRa style fine-tuning does not need that many samples. But what does matter is data quality. And so spending some time manually reviewing your samples, looking through them one by one, like building a little widget or a Gradio UI or something where you can just skim through, delete the ones that you don't like or that make mistakes, adding some heuristics like looking for repeat answers, looking for answers that are actually from the test set. If you're using few-shot prompting, you could get some like data contamination that way. Just spending some time like pruning and cleaning and filtering that data. And then if need be, training another model to do a second round and getting this data flywheel going, extremely powerful. Okay, and again, the same tricks apply, like having some sort of quality or manual view or evaluation, experimenting, reviewing, same strategy. That iterative mindset really applies throughout the whole pipeline. Okay, fine-tuning is magic. I think the others have also made this pretty clear. The libraries and tools are getting better and better and better, such that it didn't really feel like too much of a hindrance to be working mostly on a single GPU at home in my basement. The combination of LoRa with quantization, with gradient checkpointing, CPU offloading, all of these tools mean that, okay, it might be a little slower, but really you aren't too limited, even if you want to try experimenting with these really large models, like the 70 billion parameter models or the, 13, 34 billion parameter models, things that not too many years ago just felt completely out of the realm of possibilities. So I'm very excited by that trend. I did want to flag though, just like Boris was highlighting, you don't want to go to that large scale too early. One of Jeremy's big mantras throughout this whole thing was we need to get a tight iteration cycle. We need to be able to test an idea in a couple of hours, overnight max. We don't want to be committing, wasting several days waiting for a training run to finish just to test an idea. And so starting at the small models and then right at the end, literally the last few days of the competition, scaling that up. And I think that's a good parallel for a lot of other training things. You can validate your ideas really easily locally, validate them zero shot first of all, then do some very quick fine tunings on very small amounts of data. And only once you're like convinced that that's working, but you need a bit more, that's when you would, generate even more data, go to a large model, etc. Okay, one thing that was constant throughout the competition that I found interesting was that the hard parts went the hard parts. And what I mean by that is you would think that, training a 15 billion parameter LLM would be extremely difficult. But actually, there's tons of libraries available. There's lots of example code. That turns out to be almost trivial, right? Fiddling with the learning rate and things does affect performance a little bit. But especially here where we mostly just wanted to extract the latent knowledge that the model already had and make sure that it followed some format. It was very robust to different ways of training and different hyperparameters. So that turned out to be somewhat easy. Where a lot of our time ended up being wasted was things like the Kaggle competition has very limited RAM, like I think only 14 gigs of CPU RAM and 16 gigs of GPU RAM. And so getting these larger models on there, loading without running out of memory, finishing running before the timeout, installing nicely without access to the internet, so you have to put all the relevant packages in. All of this kind of admin bits stacked up. Additionally, things around data. Again, my repeated plea, look at your data, please. The number of times that I had to redo something or wasted some time, or I stopped myself having to do that by actually doing the thing that I'm going to ask you to do. Taking the batch of data just before it goes through your model's forward pass, or as close as you can get to that, decoding those tokens and manually inspecting them. That's kind of like one of the most important debugging steps, just because, you realize I left out the end of sequence token, or I accidentally left the answer in, or we said context and then we don't put the context in, or if we do put the context, it's being truncated incorrectly. The prompt format that we're using is different to the one that the model was trained on. So many issues can come down to those mismatches that it's not like traditional software where you make a mistake, it doesn't compile. the model still probably does okay, but maybe it's 70% accurate instead of 74% accurate because you have some leading or some trailing spaces, which mean that the probabilities are thrown off by that. Yeah, even things like the token for yes capital versus yes lowercase versus yes with a trailing space or a leading space, you can make the assumption and run with it and it does okay. But if you spend the time to inspect the tokens just before they go in, to generate with the model a few times and see which tokens it responds with, to maybe combine, the logits for multiple versions of the token for yes, subtract the logits for multiple versions of the token for no. All of these tricks that you only will even become aware of if you're inspecting the data right at that tokenized just before it goes into the model level. Those are where it becomes like, that slight edge from inspecting the data. One final thing I should mention just on that theme of browsing the data. Almost all the data sets that I've looked at, from refined web to any of the like open web data sets, are atrocious. If you actually just view samples, you say, how can a model learn anything from this garbage? And even the Wikipedia dumps that many of the people throughout most of the competition were using, they have things like these, any values, any formulas, any special like sections in the text often had their little expression syntax that requires a custom like Lua parser to interpret. And so you'd have the article, the context that people were fetching, say things like decay energy for this process is full stop, right? The value wouldn't be included because they'd done the parsing wrong. And yeah, that's just another thing that if you're just running it, it probably works fine. It often can guess the right answer anyway. But if you sit there and look at your data, like you manually inspect, print out, tokenize a .decode of your batch, you say, hey, hang on a minute, there's no values in this. And so we had to write our own sort of special parsing and logic to take the raw Wikipedia dumps and process them and make sure that those values are actually left in and all the other special tags and things are dealt with properly, compress those, embed them, etc. So yeah, really like surprising. Those are the hard parts, not the training the big models, which you would think is the hard parts. Okay, so some takeaways. Reminder, if you've got questions, I can speak a lot more about any of those things, but I did want to keep this as short as possible. Short feedback loops, ultra important for quickly iterating and coming to better performance much faster than if you're spending all your time on one giant fine-tuning run. That rapid iteration is very powerful. Good data flywheel is very powerful. Lots of different cases you can achieve this quite easily. Generate a few samples, train a model to generate more samples, filter them for quality, maybe make an automated filtering, train a new model. This repetition is very powerful. One thing that was lovely with this competition, and if you don't have like clients asking you to do this or a company that has a use case, I'd highly recommend finding something like this, is that it gives you like a testing ground for any new research that you're trying to understand. So a paper would come out that says, we're improving factuality in language models by contrasting the predictions from later layers, like deeper layers of the network versus earlier layers that are more focused on syntax. Hey, it takes like 5 minutes to read that paper and to, test it out on this competition that I know. I already have the evaluation. I already have the training, everything all set up. Add in this new technique, and you can see the results. We had some questions, Jeremy and I, about memorization, like how fast do these models memorize the samples shown in fine-tuning, which has relevance for test set leakage and downstream usage. As soon as you have a pet project like this, it's really fun because you straight away have something that you can slip in those experiments to. You have all the infrastructure there ready. So that was a great takeaway. Having something like this that you're tinkering with all the time, extremely powerful, even if it feels like, I'm just building Jarvis for my computer or some dumb little assistant for my company. Look at your data. Again, I'll keep saying that because it seems like that's the most important thing in this whole field. The tooling's getting better. If you are interested in the Kaggle competition, go check the discussions. It's a whole different niche. Actually winning a Kaggle competition, ensembling many different models, trying like 5 or 6 different retrieval techniques, and then combining them together, training like meta models that look at all the predictions from all the different submodels and choose which one to go with based on the type of question and the format and so on. So really fascinating look there. But more generally, I just thought this whole exercise, this really does cover, seems like a large proportion of LLM products and projects are going to follow something like this path, where you begin iterating at 0 shots, you do some fancy prompt engineering, you add something like retrieval, you try different fine-tuning strategies, And that flow, if you can do this on the Kaggle competition, you can do this for another more impactful project. And it really does seem like this is the recipe that's emerging for how to build useful things based on these incredibly powerful base models.
Fantastic. 4 out of 4. Phenomenal talks. Thank you so much, Jonathan. I'm going to bring everybody on. Just thank you guys all so much. This was a really, really incredible talk. Also, this came up a number of times from kind of everybody who spoke, but Weights and Biases actually is sponsoring this talk. So a huge shout out to them for helping make this possible. So that was really lucky or nice that everyone just happens to already be using Weights and Biases. I don't really know anybody who doesn't, but if you're not, trying out, they're fantastic. But yeah, I think we're going to have to close it because we are very over, but these were really, really awesome talks. Thank all of you so much.
Thank you.
Everybody.
Thank you.